Hello everyone. This video is about orthogonal vectors and properties of orthogonality. So let me remind you a few things that we said last time, and let's get started with a couple definitions. First of all, I remind you that two vectors are said to be orthogonal or perpendicular if their dot product is zero. Now, we can give the same definition for a set of vectors, not necessarily two of them. We say that the set of vectors is orthogonal if for any pair of vectors in the set, those two vectors are orthogonal. So an orthogonal set is a set of vectors that are 2 by 2 perpendicular to one another. Moreover, we say that S, a set of vectors, is orthonormal if it is an orthogonal set and each one of its components is a unit vector. Let's see. In this example, we have that the vector S is orthogonal. How can we, the set of vectors S is orthogonal. How can we check that? Well, we need to check that any pair of two vectors is orthogonal to one another. If I take v1 dot v2, that is 1 times 1 plus 2 times 1 plus 3 times minus 1, and that's 0. Similarly, I'll have to check v1 times v3, dot v3, and here is 1 times 5, 2 times minus 4, it's -8, and 3 times 1 is 3, so this is also 0. And the third thing to check is the third possible couple, v2 and v3. 1 times 5 is 5, 1 times minus 4 is -4, minus 1 times 1 is -1, and that's 0. So these show that S is orthogonal. However, S is not an orthonormal set because its vectors are not unit vectors. And as a matter of fact, we can double check that. For example, if I take v1, the norm of v1 is given by 1 plus 4 plus 9 over square root, which is square root of 14, which is certainly not equal to 1. And this is enough to disqualify S from being orthonormal, but let's compute the norms of the three vectors because we'll use them in the next example. The norm of v2 is the square root of 1 plus 1 plus 1. I have to square its components, so the -1 becomes a plus, and that's square root of 3. And the norm of v3 is the square root of 25 plus 16 plus 1. And that makes it the square root of 42. All of these lengths are not 1, so any one of these vectors disqualifies S from being an orthonormal set. However, something that we can always do is that given any orthogonal set, we can construct an orthonormal one simply by normalizing the vector. Remember that if I take any vector v, in this case v1, I can replace it by itself rescaled by its length, and in doing so, I obtain a unit vector because any vector divided by its length has length 1. So in our specific example, what we can do is to divide the vectors by their length. The length of v1 we computed in the previous exercise is 1 over square root of 14. Well, the length is square root of 14, so we divide by that, and we define a vector u1 accordingly. u2, in the similar fashion, will be the vector v2 divided by its length, which is 1 over square root of 3, 1, 1 minus 1, and u3 will be v3 normalized to being a unit vector, which is 1 over root of 42 times 5, -4, 1. Okay, so after doing this manipulation of dividing every vector by its norm, we get a different set as twiddle, and I'll write its entries here. This time I'll write them as vectors, so without the scalars in front. 2 over root 14, 3 over root 14, comma, the second vector will be 1 over root 3, 1 over root 3, minus 1 over root 3, and the third vector will be 5 over root 42, minus 4 over root 42, and 1 over root 42. This new set, as twiddle, is now an orthonormal set, because rescaling vectors doesn't change their orthogonality. It will rescale their dot products, but they will stay still constant times 0. So they will remain orthogonal. But now we normalized it so that every vector is a unit vector, so S twiddle is orthonormal. These notions are important because of the following fact. Any orthogonal set is a linearly independent set. We'll see why in this argument here. So if I have a set of orthogonal vectors, I have to prove that they are linearly independent from one another. So let's suppose to have such a set, v1, vn are orthogonal vectors, and let's take a linear combination which is equal to 0. Our goal to prove linear independency is that we want to show that all of the CIs are 0. How can we do that? Well, if we're writing the 0 vector like so, I will, well, we can do the following thing. I take both sides of this equation and dot them with the vector v1. So the 0 here stands for a 0 vector, so I'll dot them with v1. And I get that 0, which is the dot product of 0 times v1, is equal on the other side of whatever I get from this expression here. I can distribute the dot product, so I get c1 times v1 dot v1 plus c2 times v1 dot v2 all the way up to cn times v1 dot vn. Now, by orthogonality, we know that v1 is orthogonal to all other vectors in the set. So all of these and everything in the middle here is equal to 0 by orthogonality. So what we're left with after using the assumption that we are orthogonal is the following expression. We have that 0 is equal to c1 times v1 dot v1. Now v1 dot v1 is nothing but the norm of v1 squared. And in this fact here, we are assuming that vectors are non-zero. But if you have a non-zero vector, then its norm will be non-zero as well. So this is different from 0, since v1 is different from the 0 vector. But then the only way that I have c1 times something non-zero equals 0 is that c1 itself is equal to 0. Now, we can repeat this argument by multiplying with any of the VIs instead of the V1s. So I could replace here a VI and dot it with VI here as well. The same argument would show then that CI is equal to 0 for all possible indices I. In other words, we showed that the vectors v1 through vn are linearly independent because all of the coefficients in a way of writing 0 are all 0. Okay, so we've seen that orthogonal sets are automatically linearly independent. So if they are a generating set, there are bases, and we will talk about orthogonal bases at that point. The importance of an orthogonal basis is the following thing. There actually is a formula to find the coefficients of any vector in terms of an orthogonal basis. So what I've written here is that if you have a basis v1 through vn, which is orthogonal, then since it's a basis, you know that you can write any vector u as a linear combination of the v1s and vn through vn's. But since it's orthogonal, we actually have a formula for the coefficients. So we can find a way to write any vector as a linear combination of these explicitly, knowing what the CIs are. So how does the formula work? Well, let's do the computation here. The idea is very similar to the one that we did before. Suppose you have a vector u and you write it as a linear combination of these coefficients. Now let's dot both sides of these equations, maybe with v1. And I can dot them on different sizes because the dot product is commutative. So on this side, I get v1.u. That's okay. In here, I get an expression similar to what we obtained before. C1 dot v1 plus v1 plus C2 dot times v1 dot v2 all the way to Cn times v1 dot vn. Here we go. Again, we can use orthogonality of our bases to get rid of all of the dot products of v1 with the other vectors in here. So all of these disappear. What we're left with is just v1.u equal to c1 times v1.v1. So rewriting in a different way, we get that c1 is v1.u divided by v1.v1 is nothing but norm of v1 squared. Then one can repeat the same argument with vi's. So dotting both sides of the equality with vi. And what one obtains is the following formula. Every one of the coefficients is given by u dot vi over the norm of vi squared. Let me just remark about this. We have seen expressions like this before when we were talking about projections of vectors onto some other vector. In particular, if we look at the decomposition that we just obtained, so ui will write like this in terms of v1 through vn. Each one of these is the projection of the vector u onto, well, in this particular case, it's v1. This other one is the projection onto v2, and so on until we project onto vn. So this is a particular feature of orthogonal basis, that every vector decomposes as the sum of its orthogonal projections to one of the vectors of the basis. We've seen this phenomenon without giving it much thought using the usual coordinate axes. If you think about coordinate axes in R3, or maybe even simpler in R2, you see that every vector in R2 decomposes as the sum of two vectors, which are its projection onto one of the axes and its projection onto the other one of the axes. What is happening with an orthogonal basis is very much the same. Orthogonal bases work they're nice bases because they work like coordinate axes in this respect. In the next video, we'll see a procedure to start from any basis and modify it to make it orthogonal. It's called the Gram-Schmidt orthogonalization process. I'll see you in the next video.